In 2012, a spacecraft at the edge of the solar system recorded something so strange, scientists wrote it off as space weather and filed it away. For 13 years, that data sat forgotten in a NASA archive. Then, in 2025, we discovered an interstellar comet, and when we traced its path back in time, we realized it was in the exact same place, at the exact same moment. The conclusion is inescapable. Our oldest probe met a visitor from another star, and we've had the proof the entire time. There is a silent witness drifting through the interstellar dark, a piece of 1970s engineering now further from home than any other human creation, and for over a decade it has held a secret in its aging memory banks. This is the story of a message we received but did not comprehend, a signal buried under the assumption of noise and the celestial traveller that might have been its source. It begins not with a flash of light or a dramatic collision, but with a series of numbers on a screen that refuse to behave. August 2012. After a 35-year odyssey past Jupiter and Saturn, Voyager 1 finally crosses the heliopause. It is a moment of profound human achievement, the first machine to leave the sun's cradle and enter the realm of the stars. But the data streaming back across 17 light hours of space tells a story of chaos, not clarity. In the mission control rooms at the Jet Propulsion Laboratory, engineers and scientists watch as the magnetic field readings, which were expected to rotate smoothly into a new alignment with the galactic field, instead jump and spike erratically. The plasma wave instrument measuring the density of charged particles records surges that look less like a boundary and more like a localized storm. The anomalies are sharp, coherent across multiple instruments, and transient, lasting hours, not days. They feel like an event, not a transition. The team gathers, debates, runs models. The simplest explanation, the most conservative one, wins out. It must be turbulence at the heliopause. The boundary is complex, poorly understood. Strange things happen. The anomalies are noted, filed away in reports and relegated to the category of unsolved but ultimately unimportant curiosities. The world celebrates Voyager's entry into interstellar space, and the story moves on. Now, pull the camera back through time and space to July 2025. In a data stream from a routine sky survey, an astronomer notices a faint moving speck. It is not where it should be, and it is moving too quickly. Alerts go out, telescopes across the globe swivel. Within days, the verdict is in: we have a visitor. Designated 3I Atlas, it is a comet, but its orbit is violently hyperbolic. A steep, high-speed arc that declares its origin is not from our solar system. It is falling inward at a breathtaking 60 kilometers per second, unbound by the sun's gravity, a passerby from an alien star. As astronomers frantically calculate its path, tracing its line, backwards through the solar system, a disturbing synchronization emerges. That hyperbolic path, when projected backwards, intersects the region of the heliopause not in the distant past, but around 2012, possibly 2013, the very window of time when Voyager 1's instruments screamed their strange, brief song. The coincidence is astronomical, in every sense of the word. It raises a question that transforms curiosity into a thrilling possibility. What if the simplest explanation was wrong? What if the turbulence was not the boundary itself, but something crossing it? What if Voyager 1, our venerable scout, didn't just cross a line, it had a close encounter? So if you're captivated by this idea, that we might have to rewrite a chapter of history based on data we already had, then you need to be part of this search. I want you along for every step. Go ahead and like this video, and make sure you subscribe to this channel. This story will unfold over multiple deep dives, and I don't want you to miss a single piece of the puzzle. And tell me in the comments, where are you watching from right now? What time is it in your corner of the world? Do you think we've been missing the forest for the trees, ignoring signals because they didn't fit our expectations? This is the core of our investigation. This is not about crafting conspiracy. It is about following evidence that has been publicly available but contextually invisible. The discovery of 3I Atlas provides that missing context. It turns archived anomalies into potential clues. It invites us to be detectives on a cosmic scale, to reinterpret the past with new eyes. This is part 1, the alignment that changes the story. To understand the gravity of this coincidence, you must first step into the shoes of the people who lived it. Imagine the scene at JPL, the year 2012. The Voyager team, a group of scientists who have spent their careers with this mission, are witnessing its crowning moment. But the data is messy. There's a pressure to narrativize a clean story for the public, for history. Voyager has left the solar system. The complex, spiky reality of the sensor logs complicates that clean story. So, the anomalies become footnotes. They are the turbulence expected at a boundary. The human brain is brilliant at pattern recognition, but it is also brilliant at dismissing patterns that don't fit an established model. The model in 2012 was the heliopause. The model did not include interstellar comets, because we didn't know they could be so common. Fast forward to the Observer in South Africa in 2025, their model of the solar system now includes Oumuamua and Borisov, two confirmed interstellar visitors. When 3i Atlas appears, they are not just tracking a comet, they are tracking a member of a new class of object. Their mindset is different. They are primed to ask, "Where did you come from?" And the answer points directly back to a zone of space where, 13 years prior, our only physical probe recorded something inexplicable. Two timelines, separated by over a decade, snap together with the force of a magnetic connection. The question is no longer what caused these spikes, but who else was there? This documentary series is a forensic reconstruction. We will spend the next 2 hours dissecting this mystery. We will plot Voyager's exact coordinates in August 2012 against the uncertain backward propagation of 3i Atlas's furious trajectory. We will scrutinize the bizarre 2024 telemetry glitch that corrupted Voyager's data system, asking if it was merely aging hardware or the delayed symptom of an older, stranger encounter. We will go line by line through the published logs of the magnetometer and plasma wave science team, looking for the signature of a passing body, and we will expand our view to ask what this means for our place in the cosmos. Are we in a quiet neighbourhood, or is our solar system a crossroads for galactic debris, constantly buzzed by visitors we lack the sensors to see? The implications are profound. By the end of our investigation, you will possess all the same evidence the experts have. You will see the compelling, unsettling alignment. You will feel the weight of the unanswered questions, and you will have to decide, is this a chain of incredible coincidences, or is it the first glimpse of a solar system far more populated and dynamic than we ever dreamed? Once you see the geometry, once you grasp the timeline, it becomes a lens you cannot remove. Something passed through the frontier in 2012. Voyager 1 was there, and it recorded everything. To move beyond suspicion into the realm of credible hypothesis, you need geometry. Cold, hard, spatial geometry. You need to know not just that two objects were in the same general neighbourhood of the solar system at the same general time, but whether they were close enough for one to have left a fingerprint on the other. This is a forensic exercise in celestial mechanics. We must reconstruct the exact position of Voyager 1 during those turbulent weeks of August 2012, and we must wind back the furious hyperbolic path of 3i Atlas to see where it might have been. Only when these two trajectories are drawn on the same map can we ask the real question: could they have crossed paths? Let's begin with the known entity, Voyager. 1. By August 2012, this spacecraft had been in constant motion for 35 years. Launched in 1977, it used gravity assists at Jupiter and Saturn as a slingshot, hurling itself upward and out of the plane of the ecliptic at about 17 kilometers per second. It is a trajectory governed by momentum and the fading pull of the Sun's gravity. It has no fuel for course corrections, no ability to maneuver. It is a bullet whose path is exquisitely predictable. On that August day, Voyager 1 was approximately 122 astronomical units from the Sun. An astronomical unit, the average distance from Earth to the Sun, is about 150 million kilometers. This means Voyager was over 18 billion kilometers from home. Its position is not an estimate. It is a precise coordinate known to the teams at NASA's Deep Space Network. A global array of gigantic radio dishes tracks the spacecraft continuously, measuring the Doppler shift of its signal to determine velocity, and using triangulation to fix its location in the three-dimensional void. We have ephemeris data, the celestial equivalent of a flight log, that tells us exactly where Voyager was hour by hour as it punched through the heliopause. We can place it as a tiny, brilliant point of human ingenuity in the vast, dark ocean beyond the Kuiper Belt, headed northward toward the constellation Ophiuchus. Now we must place the stranger 3I Atlas. This is where certainty gives way to calculated uncertainty. The comet was discovered in July 2025, already within the orbit of Jupiter, about 4.5 astronomical units from the Sun and inbound. The initial frantic observations, multiple telescope sightings over several nights, allowed astronomers to calculate its orbital elements. Its eccentricity, greater than 1, confirming its hyperbolic unbound nature, its inclination, steep telling us it came from well off the solar system's plane, its perihelion distance, and its argument of perihelion. These 6 numbers mathematically define its path through space. With these elements, you can run the clock backwards. This process, called backward propagation, is standard astronomy. You take the comet's current velocity and position, apply the laws of gravity, primarily the Sun's pull with minor tweaks from the planets, and simulate its path into the past. But here lies the rub: uncertainty. Every measurement from Earth has a tiny error bar. The comet's position is not a perfect point, it is a fuzzy probability cloud. When you project that cloud backwards over 13 years, the cloud expands. The further back you go, the less precise you can be. The observational arc for 3I Atlas in 2025 was only a few months long, good enough for a rough backward projection, but terrible for pinpoint precision to within a few million kilometers in 2012. Furthermore, comets are not simple gravitational test particles. They are active, they outgaze. Jets of sublimating ice act like tiny thrusters, nudging the comet off a purely gravitational path, a phenomenon called non-gravitational acceleration, which we will delve into deeply later. If 3I Atlas was active back in 2012, even minimally, our simple backward projection could be significantly off. So, where does the rough calculation point? Despite all these caveats, the answer is consistent and unsettling. When you run the numbers, the probable path of 3I Atlas places it crossing the region of the heliopause around 2012 or 2013. The margin of error might be a year or more, but it points squarely to that epoch. The ballpark alignment is undeniable. Now, picture the map, not a flat two-dimensional drawing, but a three-dimensional model of the outer solar system. The Sun is a tiny point at the centre. The orbits of the planets are negligible rings far inward. You're focused on the distant frontier, about 120 AU out. Here, the solar wind, a stream of charged particles blowing from the Sun, finally slows from supersonic to subsonic at a shock front, and further out, it balances against the pressure of the interstellar medium at the heliopause. This boundary is not a perfect sphere. It's a blunt, asymmetrical bubble, stretched in one direction by the Sun's motion through the galaxy. Voyager 1 is a dot on the northern flank of this bubble. Meanwhile, from some distant angle, perhaps from below the ecliptic, another dot is approaching at 60 kilometers. This is 3I Atlas, moving so fast its path is almost a straight line on this scale, arcing slightly under the Sun's gravity as it plunges inward. 2 specks, one human-made, one a primordial relic from another star, on courses that may bring them into proximity. Crossing paths does not mean a collision. Space is vast. The odds of a physical impact are infinitesimally small. But proximity is a different matter. If 3I Atlas passed within even a few astronomical units of Voyager 1, that's still hundreds of millions of kilometers, and if it was active, it could have created a localized disturbance in the magnetic field and plasma environment. A comet's coma, when ionized by solar and cosmic radiation, forms a plasma cloud that interacts with the ambient magnetic field, creating a draping effect and a magnetotail. Voyager's instruments, specifically the magnetometer (MAG) and the plasma wave instrument (PWS), are designed to be exquisitely sensitive to such changes. A passing comet could register as a sharp, coherent spike in magnetic field strength and plasma density, a transient event lasting hours or days, exactly the kind of turbulence that was observed. So, the geometric possibility exists. The question transforms from could it have happened to what would the signature look like, and does it match the anomalies in the data? To answer that, we must leave the clean world of orbital mechanics and dive into the messy, complex and still debated data from Voyager's historic crossing, data that, to this day, holds unexplained mysteries. In late 2023 and into 2024, as astronomers were buzzing with the discovery of more interstellar objects, and the impending characterization of 3I Atlas, Voyager 1 itself began to falter. It developed what NASA engineers called a telemetry glitch. The spacecraft's Flight Data System, FDS, the onboard computer responsible for packaging science and engineering data for transmission, began sending back gibberish. The signal was strong, the carrier wave was healthy, but the data itself was corrupted, a stream of meaningless ones and zeros. For the small, dedicated team that keeps Voyager alive, this was a crisis. They initiated a grueling, slow-motion troubleshooting process. A command sent from Earth takes over 22 hours to reach Voyager. The response takes another 22 hours to return. Each diagnostic cycle is a 2-day exercise in patience. Eventually, they traced the problem to a single corrupted memory chip within the FDS. Through ingenious software workarounds, they rerouted functions, and by mid-2024, they had restored coherent communication. The official explanation was straightforward and logical. Age. Voyager 1 is, as of this writing, 47 years old. Its technology is prehistoric. Its computer memory is measured in kilobytes. It has been bombarded for decades by cosmic rays and extreme temperature swings. Components degrade, bits in memory chips flip. The fact it works at all is a miracle of engineering. To suggest anything other than random hardware failure seems like fanciful thinking. But in a detective story, timing is never just a detail, it's a potential clue. The glitch manifested right as scientific and public interest in interstellar objects was reaching a new peak. Voyager 1 is the only human object in a position to have physically encountered such a visitor in the distant reaches, and then its system for telling us about its environment fails in a novel way. Coincidence? Almost certainly, most scientists would say, but we must ask, what if the failure wasn't entirely random? What if it was a delayed consequence, or a final symptom of an earlier trauma? Consider the environment Voyager lives in. The heliopause region is not benign. It is a maelstrom of magnetic fields and high-energy particles. Now, imagine introducing a new element, an active interstellar comet. A comet's coma is a source of complex chemistry and additional plasma. Its interaction with the heliopause's magnetic fields could generate localized regions of intense electromagnetic activity. Could a severe enough plasma disturbance, a kind of space weather event caused by the comet's passage, have induced electrical currents or voltage spikes within Voyager's decades-old wiring? Could it have accelerated the degradation of a sensitive memory chip? It's a stretch, but not physically impossible. Spacecraft anomalies often have root causes that are only understood years later. Or, consider a more speculative possibility. What if the FDS corruption was not just a failure, but an overload? What if, in 2012, Voyager's sensors recorded data so far outside their design parameters, a magnetic field signature or plasma oscillation pattern never seen before, that it was stored in memory in an unusual way? Over the ensuing years, as that memory sector was occasionally accessed, or as radiation-induced bit errors accumulated, it could have eventually corrupted the file system's indexing, leading to the 2024 collapse. This is the realm of software ghosts, but it speaks to a broader philosophical point. How do we distinguish between a machine malfunctioning and a board machine detecting something truly novel? When Voyager sends back data that confounds our models, we have two choices: assume the spacecraft is broken, or assume our models are incomplete. The safe choice, the conservative choice, is always to suspect the hardware. But history shows that occasionally the second choice is correct. The heliopause crossing itself was one of those times. The models were wrong about its complexity. Perhaps the 2012 anomalies represent another such moment, and the 2024 glitch is a tragic coda, making it harder for us to retrieve the full truth. The glitch adds a layer of urgency to re-examining the older data. With each passing year, Voyager's power dwindles. Its systems are being shut down one by one to conserve energy. Sooner than we'd like, it will fall silent forever. If there is a message from 2012 buried in its archives, we have a limited window to decode it before the only witness to the event is gone. The 2024 incident is a reminder that this data stream is finite and fragile. It forces us to ask, what precious signals might we have already lost in that corrupted data? And what might we still save if we look with fresh eyes? To understand what Voyager might have felt, we must descend into the numbers. The published data from the magnetometer, MAG, and plasma wave science, PWS instruments during the August 2012 crossing are a testament to scientific transparency and to enduring mystery. The story science wanted to tell was clean. Voyager crosses a boundary, the magnetic field direction shifts from a solar orientation to a galactic one, plasma density drops as solar wind particles vanish, and the cosmic ray count from outside surges. This did happen, but not as a single crisp event. It was a messy, drawn-out, and puzzling transition. The magnetic field data is particularly telling. Scientists predicted a clear rotation, a definitive change in the field's direction, as Voyager left the Sun's magnetic domain and entered the interstellar magnetic field, which is tilted at a different angle. What they saw instead was chaos. The field direction oscillated wildly for weeks. There were sharp, temporary spikes in field strength that didn't align with any smooth model of a boundary. Some of these spikes lasted only a few hours. They looked less like a global boundary reorientation and more like localized magnetic knots or brief intrusions. The plasma wave instrument told a similar story. It detected bursts of oscillation, sharp rises in plasma density that would peak and then rapidly decay. The official scientific papers proposed explanations within the framework of heliophysics. Perhaps the boundary is multi-layered, with multiple crossing points. Perhaps there are magnetic ropes and reconnection events. Perhaps the heliopause itself is a turbulent zone of mixed plasma. These are all valid and plausible hypotheses from experts in the field. But over a decade later, no single model fully explains the specific transient nature of some of the largest anomalies. The data retain loose ends. Now, introduce a new variable, a moving point source of disturbance. Imagine 3i Atlas, even if only weakly active, approaching the heliopause. As its ice is sublimated in the slightly warmer environment just inside the boundary, it would have generated a coma of gas. This gas, ionized by cosmic radiation, becomes a plasma. This plasma carries with it a magnetic field, either from the comet itself or, more likely, the interstellar magnetic field it has brought with it, now draped around the obstacle. This creates a mini magnetosphere around the comet, a bubble of distorted magnetic field lines and enhanced plasma density. If Voyager 1's trajectory intersected this bubble, even skimming its outer edge, the instruments would have recorded a very specific signature. First, the magnetometer would see a sudden increase in field strength, a deflection in field direction, as the lines drape around the comet, and then a return to the background interstellar field. This would be a coherent, structured pulse, not random noise. Second, the plasma wave instrument would see a corresponding spike in electron density, a sharp rise and fall. The timing of these two signals would be synchronized. This is exactly the kind of transient localized anomaly that was so puzzling in 2012. The event would be brief because of the comet's immense speed. At 60 km relative to a nearly stationary Voyager, even a large interaction region hundreds of thousands of kilometers across would be traversed in a matter of hours. The data would show a clean, needle-like pulse, not the broader, more chaotic waves expected from large-scale boundary turbulence. There is, however, a significant problem with this comet hypothesis: dust. An active comet sheds dust grains. If Voyager had flown through a dust coma, even a tenuous one, it should have registered micrometeoroid impacts. Voyager does not have a dedicated, sensitive dust detector like some other missions. It relies on the plasma wave instrument to detect the ionization trails of dust impacts, a method that is not its primary function and has limitations. No clear evidence of a dust shower was reported in the 2012 data, but this is not a fatal blow. Perhaps 3i Atlas was not yet producing significant dust in 2012, only gas. Its unusual carbon dioxide-rich composition might sublimate without releasing large dust grains initially. Or perhaps the dust was there, but the signal was too faint or misinterpreted within the complex plasma data. The absence of a dust signal doesn't rule out an encounter, it merely fails to confirm it. The challenge, and the opportunity, now lies in a deliberate reanalysis. Someone needs to go back to the raw, high-resolution MAG and PWS data from August and September 2012. They need to look not for boundary transitions, but for isolated, coherent pulses. They need to cross-correlate the magnetometer spikes with the plasma density spikes, searching for coincidences that define a single passing event. They need to model what the magnetic and plasma signature of a small, fast, hyperbolic comet would look like and see if any of the anomalous data fits that shape. No one has done this systematically because until 3i Atlas arrived, there was no reason to. The comet provides the motive to reinterpret the evidence. The archived data is the crime scene. The question is whether we can find the fingerprint of the visitor. Let us shift our perspective entirely. Imagine you're an archaeologist, but your dig site is not in the desert. It is in the petabyte archives of NASA's planetary data system. Your artifact is not a pottery shard, but a string of numbers, a timestamp, a magnetic field strength in nanoteslas, a plasma frequency in kilohertz. You are convinced that within these terabytes of telemetry from Voyager 1, there is a message, a coherent physical event that was recorded but never decoded because we lacked the cipher. This is the undecoded message hypothesis. It posits that Voyager has already told us about 3i Atlas or something like it, but the information is trapped in a format we dismissed as noise. Decoding it means looking for patterns that violate the expectation of randomness. The first step is correlation. In the noise of space, true signals often appear across multiple independent sensors. Did the magnetometer spike at the exact same time the plasma wave instrument detected a density increase? Did the low-energy charge particle detector see a coincident fluctuation? If multiple instruments register an anomaly within a tight time window, say 1 hour, the probability that its random instrumental noise plummets. It becomes a correlated event, something real happening in the environment around the spacecraft. The next step is coherence. Random noise is just that, random. It has no shape, no beginning, middle, and end. The signature of a passing object would have a structure. If you plotted magnetic field strength over time, you would see a curve, a gradual rise as Voyager approached the comet's influence, a peak at closest approach, and a symmetrical fall as it receded. The plasma density would follow a similar matching curve. The duration of the event would be consistent with the relative speed and size of the interaction region. You would be looking for a bump in the data that has a defined Gaussian-like profile, standing out from the chaotic flat baseline of the heliopause turbulence. Then you look for internal structure. A comet's magnetotail isn't a smooth cloud, it's filamented, full of density variations and current sheets. As Voyager passed through, it might not record one smooth peak, but a primary peak with smaller oscillations superimposed, like riding over a series of waves. This kind of complex repeating pattern within a larger envelope is another hallmark of a structured object, not amorphous. Boundary chaos. The obstacles to this kind of analysis are significant. Data decay is a real issue. Over years, data formats become obsolete. Raw, high-resolution datasets might be stored on outdated media or in poorly documented archives. The sheer volume is daunting. Voyager has been transmitting for nearly half a century. Finding a specific 12-hour period from 2012 requires sifting through mountains of information. There's also the problem of the baseline. To identify an anomaly, you must define normal. What is the typical magnetic field strength and variability in the interstellar medium just outside the heliopause? This itself is an active area of research, and our understanding of that baseline has evolved since 2012. Perhaps what was considered an anomaly then is now seen as part of the normal interstellar fabric, or vice versa. So why hasn't this reanalysis happened? It falls between the cracks of scientific disciplines. Heliophysicists are focused on the large-scale structure of the boundary, not on hunting for comet signatures. Planetary scientists and comet experts don't typically work with Voyager's plasma data. It requires a hybrid expertise that is rare. Furthermore, proposing that a decade-old anomaly was caused by an interstellar comet is a high-risk, low-reward endeavour for a career scientist. It sounds like fringe speculation. It's easier and safer to work within established paradigms. But the discovery of 3i Atlas changes the risk-reward calculation. It provides a specific, testable hypothesis. We're no longer asking, could any unknown object have caused this? We are asking, did this specific object with this specific trajectory cause this specific data spike? That is a question that modern data science tools can begin to answer. The message is there, encoded in nanoteslas and kilohertz, waiting in the silent digital catacombs of our own data archives. It waits for someone with the curiosity, the interdisciplinary courage, and the computational tools to run the correlation algorithms, to plot the curves, and to see if the bump in the data matches the path of the comet. The undercoded message hypothesis is ultimately an argument for scientific humility. It reminds us that our probes are often smarter than we are. They record everything their sensors tell them without prejudice. It is we, the interpreters, who apply filters, who decide what is signal and what is noise. Sometimes, to hear the message, you must first admit you might have been deaf. In astronomy, there is a powerful technique called precovery, short for pre-discovery recovery. It involves searching archival images from sky surveys for an object before its official discovery date. When you find it, you dramatically extend its observational arc, tightening its orbital calculations and tracing its path with far greater precision. For a fast-moving interstellar object like 3i Atlas, precovery images are the holy grail. They could tell us exactly where it was in 2013, 2015, even 2010. They could shrink the uncertainty of its 2012 position from a blurry cloud of possibilities to a sharp line. So, where are they? The comet was discovered in July 2025 at about 4.5 AU from the Sun. For months or even years prior, it was inbound, moving through regions of space that are routinely photographed by automated all-sky surveys like Pan-STARRS, the Asteroid Terrestrial Impact Last Alert System, ATLAS, and the Zwicky Transient Facility, ZTF. These projects image the entire visible sky every few nights, generating petabytes of data, all in search of moving or changing objects, asteroids, comets, supernovae. Logic dictates that 3i Atlas, unless it was impossibly faint, should be in those images. Yet, as of now, its pre-discovery observation arc is short, only weeks before its official detection. This is strange. It suggests one of several things. First, brightness. A comet's brightness comes from sunlight reflecting off dust and gas in its coma. But comets only develop a significant coma when they're warm enough for their ices to sublimate. Far from the Sun, in the deep cold beyond Jupiter, a comet can be dormant, a dark, frozen rock reflecting almost no light. If 3i Atlas was dormant until it crossed some threshold of warmth or environmental interaction, like the heliopause, it could have been effectively invisible to surveys until mid-2025. Its sudden appearance wouldn't be a mystery, it would be a wake-up call. Second, motion and algorithm failure. Survey telescopes use sophisticated software to compare images taken nights apart. They look for dots that move in a predictable, linear way typical of solar system objects. But 3i Atlas moves with a different cadence. Its hyperbolic orbit and extreme speed might have made its apparent motion against the stars too slow or in an unexpected direction for the detection algorithms, which are tuned for main belt asteroids and Kuiper belt objects. The comet's faint smudge might have been automatically flagged as a cosmic ray hit, a camera artifact or background noise, and simply deleted by the software before a human ever saw it. Third, the solar blind spot. This is a major factor. No ground-based telescope can look anywhere near the Sun. There is a cone of sky, roughly 30-45 degrees around the Sun, that is unobservable due to glare. If 3i Atlas's inbound trajectory lay within this cone for a long period, if it was, in effect, approaching from behind the Sun from our earthly perspective, it would have been utterly hidden until its orbital motion carried it out of the glare. By the time it emerged, it would already be relatively close and bright, explaining its sudden discovery. The idea of a dormant phase is particularly compelling given 3i Atlas's unusual composition. Spectral analysis shows it is extremely enriched in carbon dioxide relative to water ice. CO2 ice sublimates at a lower temperature than water, ice. It's possible that the comet's surface was a crust of irradiated refractory material shielding volatile CO2 ice beneath. The shock of crossing the heliopause, a region of increased pressure, magnetic field interaction, and perhaps slightly warmer plasma, could have been the trigger that cracked this crust, exposing the volatile CO2 to space and igniting outgassing. This would mean the comet turned on right around the time it encountered Voyager's neighbourhood, transitioning from an invisible, dark rock to a visible, active comet almost instantly. The search for precovery images is not a trivial task. It requires sifting through terabytes of archived image data, often in proprietary formats, applying new detection algorithms tuned for hyperbolic motion, and a lot of patient, meticulous work. But it has been done before by dedicated amateur astronomers and citizen scientists. Finding even one precovery image from 2024 or 2023 would be a monumental breakthrough. It would anchor the comet's past position, allowing us to say with much greater confidence, on August 25th, 2012, 3I Atlas was here, and then we could look at Voyager's data from that exact date and location. The absence of precovery images is, in itself, a piece of evidence. It suggests 3I Atlas was a ghost until the moment it wasn't, and if it was a ghost in 2012, then the only record of its passage might not be in light, but in the magnetic and plasma disturbances it left in its wake. Disturbances that one very old, very distant spacecraft just might have felt. 3 Atlas is not just passing through, it is screaming through. A hyperbolic orbit with an eccentricity greater than 1 and a velocity of 60 km is not a gentle drift into our neighbourhood. It is the signature of a violent origin or a violent journey. Objects don't naturally achieve such speeds within a star system unless something gives them a fierce gravitational kick, like an encounter with a giant planet or a binary star. But 3I Atlas has been travelling in the interstellar void for perhaps billions of years. The kick that ejected it from its home system happened eons ago, so why is it still moving so fast, and why on this particular path that led it to our heliopause? This leads us to the perturbation hypothesis, the idea that something somewhere in interstellar space relatively recently gave 3I Atlas a nudge that aimed it directly at our solar system. What could perturb an interstellar comet? The galaxy is not a perfect vacuum. It is filled with tenuous structures. One possibility is a molecular cloud, a cold, dense region of gas and dust. While the drag from such a cloud on a comet-sized object would be infinitesimally small, over millions of years it could gradually alter its course. Another is the galactic magnetic field. The comet's ionized coma, if it was sporadically active, could interact with this field, experiencing a weak but cumulative Lorentz force. More dramatically, a passing star could have done it. Stars in the galaxy are in motion, and close encounters, while rare on human timescales, are common over billions of years. The gravity of a star passing within a light year or two could significantly deflect a slow-moving comet, like a billiard ball striking another. Or perhaps the perturber was a shockwave from a relatively nearby supernova, a blast of energy and particles that could have physically pushed on the comet's surface or its coma. Now connect this to the heliopause and Voyager. The heliopause itself is a shock front, a place where the supersonic solar wind slams into the interstellar medium and suddenly slows. It is a region of immense pressure, magnetic field compression, and turbulence. What if the final critical perturbation that set 3I Atlas on its precise inbound course happened right there? Imagine the comet approaching the solar system on a trajectory that would have sent it skimming past the heliosphere. As it enters the complex pressurized environment of the heliopause, the interaction could act like a gravitational lens made of pressure and magnetism, giving it a slight sideways kick that alters its angle just enough to send it plunging inward. This same violent interaction could have been the trigger that woke the comet up. The increased pressure, the collisions with heliopause plasma, or the shifting magnetic fields could have fractured its dormant crust, initiating the outgassing that would later make it visible. In this scenario, Voyager 1 was not just a passive observer near the scene of a passing comet, it was a witness to the comet's activation. The anomalies in the data would then be a composite signal, part direct interaction with the comet's new plasma cloud, and part the comet's disruptive effect on the heliopause itself, a localized storm kicked up by the intruder. This hypothesis elegantly ties together several threads: the comet's high speed and precise aim, its sudden appearance as an active body, and the strange, storm-like anomalies Voyager detected. It suggests that the heliopause is not just a boundary marker, but an active participant in the solar system's interaction with galactic debris. It transforms the frontier from a wall into a filter, a processor, and sometimes an activator of the material that drifts into it. The compositional data from 3I Atlas supports the idea of a recent activation. Its extreme carbon dioxide enrichment and evidence of heavy cosmic ray processing speak of a surface that has been cooked by the galaxy for eons. This creates a volatile, rich but sealed layer. The heliopause crossing could have been the crack in that seal. The resulting outgassing would be sudden and vigorous, consistent with the comet appearing bright and active upon discovery. The perturbation hypothesis, while speculative, moves us from a story of mere coincidence to a story of dynamic interaction. It paints a picture of a solar system that is constantly being probed and prodded by external forces, where the boundary is a place of transformation, and where our distant probe may have recorded the moment a sleeping visitor from the galactic dark was startled awake. If we are to ever know whether 3I Atlas and Voyager 1 met, we must confront a fundamental complication. Comets are bad Keplerian objects. They don't follow the perfect elliptical paths dictated by gravity alone. They are icy, outgassing bodies, and the jets of gas and dust that create their beautiful tails also act like tiny rocket thrusters, pushing them off course. This is non-gravitational acceleration, NGA, and it is the bane of precise comet orbit prediction. For solar system comets, we have centuries of data. We've developed models that estimate NGA based on the comet's distance from the Sun, its composition, and its observed brightness. We can plug these forces into the equations and get a reasonably accurate path. For interstellar comets, we have almost no data. Oumuamua showed perplexing NGA with no visible coma, sparking endless debate. Borisov behaved more like a normal comet. 3I Atlas is the third data point, and we are still learning its behaviour. The existence and magnitude of 3I Atlas's NGA is critical for our backward propagation. If we simply rewind its 2025 orbit using gravity alone, we get one estimated position for 2012. But if the comet was outgassing significantly in the past, even far from the Sun, our rewind will be wrong. Outgassing provides a continuous, invariable push that changes the velocity vector over time. If the NGA was strong or directed in an unusual way, the comet's actual position in 2012 could be millions of kilometers away from our gravity-only projection. This uncertainty creates a cone of possibility for its past location that could easily encompass or exclude a close approach to Voyager 1. The direction of the nudge matters immensely. Most outgassing thrust is directed away from the Sun, as the heat-driven sublimation occurs on the sunward side. This generally acts to slow a comet's inward fall or accelerate its outward journey. But comets can have a symmetric activity, jets from specific spots on a rotating nucleus that can push them sideways, altering their orbital plane or argument of perihelion. The unusual carbon dioxide-driven activity of 3I Atlas might produce a different NGA profile than the water-dominated comets we're used to. So, what do we know? Preliminary analyses of 3I Atlas's orbit since discovery have not yet revealed strong anomalous NGA. It seems to be following a path consistent with a primarily gravitational trajectory, with normal comet-like outgassing forces. But the observational arc is still short. NGA effects can be subtle and become apparent only over many months of tracking as tiny deviations accumulate. It is entirely possible that future observations will reveal a small but significant non-gravitational component that changes the orbital solution. Let's construct a scenario that highlights the problem. Suppose in 2012, as 3I Atlas crossed the heliopause, the environmental shock triggered its initial violent outgassing. A powerful jet of CO2 gas erupted from a localized fissure. For a period of days or weeks, this jet provided a thrust vector that was not directly sunward, perhaps due to the comet's rotation and the fissure's location. This thrust gave the comet a slight, sideways velocity change, altering its trajectory by a tiny fraction of a degree. The comet then moved on, the jet subsided as the exposed ice sublimated away or sealed over, and the outgassing returned to a more normal sunward pattern. Fast forward to 2025. Astronomers fit an orbit to the new observations. They assume NGA has been constant and sunward, or they ignore it for the initial backward projection. Their model places the comet in 2012 at position A, far from Voyager. But in reality, because of that brief, anomalous jet at the heliopause, the comet was actually at position B, which was very close to Voyager. The geometry appears not to align because our model of the comet's past is flawed, missing a key impulsive event. This is the central challenge. We're trying to solve a cosmic who'd unit with incomplete information about the suspect's movements. The comet's path is not a clean line in the sky. It is a meandering trail influenced by the invisible force of its own evaporation. To pin down its 2012 location, we need to understand its activity history, which we may never fully know. This doesn't make the hypothesis untestable. It makes the test more nuanced. It means that instead of looking for a single perfect orbital intersection, we should be looking for a range of possible intersections based on plausible NGA scenarios. If, within the broad cone of uncertainty generated by unknown past NGA, there exists a trajectory that brings 3i Atlas into plausible interaction distance with Voyager, and if that trajectory also corresponds to a date with a major unexplained anomaly in Voyager's data, then the hypothesis gains strength. The NGA debate forces us to embrace uncertainty. It tells us that the backward orbital calculation is not a fact, but a question, and that question leads us back, inevitably, to the one place where we might find an answer independent of orbital mechanics, the sensor logs of Voyager 1 itself. If the comet was there, it left a mark. The challenge is to recognise that mark for what it is. We have been thinking of Voyager 1 as a lone witness in the wilderness, but what if it is not alone? What if it is merely the most distant node in a vast unintentional sensor network scattered throughout the heliosphere? This network includes its twin, Voyager 2, which crossed the heliopause in a different location in 2018. It includes New Horizons, out in the Kuiper Belt. It includes IBEX, the Interstellar Boundary Explorer, a spacecraft in Earth, orbit that remotely images the interactions at the heliopause by detecting energetic neutral atoms. It includes the Parker Solar Probe, diving close to the Sun, and numerous other missions at Mars, Jupiter and Saturn, many carrying magnetometers and plasma instruments. Together they form a distributed detection grid. The core idea is this: a large, perturbing event in the outer solar system, like the passage of an active interstellar comet, should not affect only one point. The disturbances it creates, whether in the magnetic field or in the population of charged particles, can propagate. Magnetic disturbances travel at the alpha speed along magnetic field lines. Pressure waves and shocks travel through the solar wind. Energetic particles can be accelerated and then travel along spiral paths dictated by the interplanetary magnetic field. If 3i Atlas's heliopause crossing in 2012 was a significant event, it might have sent ripples through the heliospheric medium that could have been detected hours, days, or even weeks later by other spacecraft. The task would be to scour the archives of all these missions for the late summer of 2012 looking for correlated anomalies. Did IBEX see a transient bright spot in its global map of the heliopause that aligned with Voyager 1's position? Did New Horizons, then still in the inner heliosphere, detect a burst of anomalous particles or a magnetic field perturbation that, when traced back along the solar wind flow, originated from the outer boundary around that time? Did the twin Voyager 2, still inside the heliopause in 2012 but on the opposite flank of the solar system, sense any correlated activity? Finding such a multi-spacecraft correlation would be powerful evidence. It would transform the Voyager 1 anomaly from an isolated, ambiguous glitch into part of a larger coherent event, a solar system-wide ping caused by an external object. This kind of multi-point sensing is how we study coronal mass ejections from the Sun. We watch the shock wave propagate from the Parker Solar Probe near the Sun, past Earth-orbiting satellites, out to the Voyagers. Applying the same technique to an inbound disturbance is a novel concept. Why hasn't it been done? Because until recently there was no putative source to justify the immense effort of time-correlating petabytes of data from dozens of missions across multiple agencies. The effort is staggering. Data formats, coordinate systems and time standards differ. The analysis requires deep expertise in several subfields of space physics. It's a logistical nightmare. But it is not impossible. Modern data science and machine learning techniques are beginning to make such cross-mission studies feasible. A targeted search, focused on a specific 2-week window in August 2012 and a specific region of space, is a manageable project for a dedicated team. Imagine the result: a scientific paper showing that on August 25, 2012, Voyager 1's magnetometer spiked. On August 26th, IBEX's data showed a localized enhancement of energetic neutral atoms from the correct direction. On August 27th, the particle detectors on New Horizons registered a faint, unusual stream of ions. When the solar wind propagation time is accounted for, all these signals point back to an origin at Voyager 1's location on August 25th. The chain of evidence would be compelling. It would argue forcefully that something happened out there that day. Something that shook the magnetic and plasma environment over a vast volume. The heliosphere as a sensor network concept reframes the mystery. It turns the problem from one of proving a single encounter to one of detecting the echoes of that encounter throughout the system. It leverages all of humanity's scattered robotic explorers as a single cohesive instrument. And it suggests that the evidence for 3i Atlas's passage, or the passage of any interstellar object, might not be buried in one dataset, but fragmented across many, waiting for someone to assemble the pieces. Our investigation hinges on a simple, unsettling truth. Astronomy is riddled with blind spots. We do not see the universe as it is. We see the slice of it that our tools and our vantage point allow. For every Oumuamua, Borisov, or 3i Atlas we catch, statistics suggest dozens, perhaps hundreds, of similar interstellar objects slip through our nets unseen. Understanding these blind spots is crucial to appreciating why Voyager's data might be so uniquely valuable. The first blind spot is depth. Our most powerful surveys like Pan-STARRS and the upcoming Vera C. Rubin Observatory are designed to scan the sky quickly and deeply, but they have a magnitude limit. An object must reflect or emit enough light to rise above the background noise. A dormant dark comet or asteroid, especially one far from the Sun, is simply invisible. It could pass within the orbit of Neptune and we would never know unless it happened to drift directly in front of a star, causing a micro-lensing event, an incredibly rare detection method. The second blind spot is velocity. Our detection algorithms are optimized for the typical motions of solar system objects. An interstellar object on a hyperbolic trajectory may move too slowly or too quickly against the stars for a standard difference imaging technique to flag it. If it's moving almost directly toward or away from us, its apparent motion is near zero. It looks like a stationary, faint star and is ignored. If it's moving extremely fast, it might blur in a single exposure or move so far between observations that the software fails to connect the dots. The third and most significant blind spot is direction. The region around the Sun is forbidden territory for telescopes. This solar exclusion zone means any object approaching from that direction is hidden until its orbit carries it out of the glare. Many potentially hazardous asteroids are discovered only days before, closest approach for this very reason. For an inbound interstellar object, it could spend years approaching from the sunward side, completely cloaked, only revealing itself when it's already relatively close. Fourth is inclination. Most surveys focus on the ecliptic plane, where the planets and most asteroids reside. An object coming in from high above or below the plane, as 3i Atlas did, spends less time in these densely monitored zones. It may pass through the survey fields, but if it's faint and moving through less frequently scanned regions, it can be missed. Finally, there is the blind spot of expectation. Until 2017, we didn't expect interstellar objects. Our models of solar system formation suggested they should be exceedingly rare. That expectation shaped our software and our analysis priorities. Even if a strange dot appeared in an image, if its motion didn't fit a bound orbit, it might have been dismissed as an artifact. Now, place Voyager 1 in this context. It operates in perhaps the greatest blind spot of all, the vast three-dimensional volume beyond Neptune. No telescope on or near Earth has the resolution to image small objects at that distance. The region is not systematically scanned. If an interstellar object is passing through that volume and is not on a trajectory that brings it dramatically inward toward the Sun, we will never see it optically. It is the perfect dark corridor for galactic traffic. Voyager 1, therefore, is not just a spacecraft. It is an unmanned outpost in the darkest part of our observational wilderness. It is the only instrument we have placed in that region that can sense the environment in ways other than light. Its magnetometer and plasma wave instrument are like a tripwire. They don't need to see an object to detect its influence. They feel the distortions in the invisible fields that fill space. This is why the 2012 anomalies are so potentially significant. If an object passed through that blind spot, Voyager was the only thing there to notice. Its data is the sole record of an event that was electromagnetically loud but optically silent. The interstellar blind spot problem reframes the entire mystery. It tells us that non-detection by Earth-based telescopes means very little. The absence of precovery images is not evidence of absence. It is the expected condition for an object waking up in the dark. It forces us to rely on the one witness we left at the scene, and it raises a profound, almost philosophical question. If our eyes are so limited, how many visitors have come and gone without a trace? How rich and busy is the darkness beyond the planets? Voyager's strange data spike might be our first fleeting answer. In 2025, as 3i Atlas was being tracked, a separate but equally enigmatic discussion was occurring in the astrophysics community, the tentative detection of a dark matter stream passing near the solar system. Dark matter, the invisible, intangible substance that makes up 85% of the universe's mass, is thought to clump and flow in vast currents through the galaxy. A team analysing subtle gravitational perturbations in the orbits of distant Kuiper Belt objects and the precise motions of nearby stars proposed that such a stream might be passing through our neighbourhood. The claim was controversial, far from proven, but it opened a door to extraordinary speculation. Could there be a connection? Dark matter, by definition, interacts only via gravity, and possibly the weak nuclear force. It should not directly affect a comet or a spacecraft's magnetometer, but the key word is directly. The gravitational influence of a dense dark matter stream could, over millions of years, perturb the trajectories of objects in the Oort cloud or the scattered disk, gently steering some toward the inner solar system. In this very indirect way, a dark matter stream could be the original perturber that set 3i Atlas, or objects like it, on a collision course with our heliosphere. More speculatively, some beyond the standard model theories suggest certain types of dark matter could interact weakly with magnetic fields or plasma under extreme conditions. The heliopause, a region of fierce magnetic shear and plasma density gradients, is certainly extreme. If a dark matter stream were passing through it concurrently with an interstellar comet, could the combination of the two, the comet's plasma and the stream's exotic physics, create an amplified or unique signature? It's a wild idea bordering on science fiction, but it underscores a broader point. The outer solar system is an environment where multiple invisible forces converge. We have the solar magnetic field, the interstellar magnetic field, the flow of galactic cosmic rays, the solar wind, and possibly streams of dark matter. A comet passing through is like a stone thrown into a pond with multiple overlapping currents. The ripples it creates will be complex. The 2025 dark matter stream hypothesis, even if later disproven, is emblematic of a shifting paradigm. It shows that scientists are beginning to consider our solar system as an integrated part of a dynamically rich galaxy, subject to influences beyond mere starlight. It encourages a holistic view where an anomaly in a spacecraft's data might not have a single, simple cause, but could be the result of a confluence of factors, a comet and the unusual region of space it's passing through. For our investigation, the dark matter connection is less a serious proposed mechanism and more a metaphor. It represents the unknown variables, the hidden forces we haven't yet accounted for. It cautions us against being too reductive. The Voyager 1 anomalies might not be a clean fingerprint of a comet. They might be the smudged composite of a comet interacting with a particularly turbulent or unusual patch of the heliopause, a patch whose unusual nature might have other deeper causes in the galactic environment. This line of thinking expands the mystery from did a comet pass by to what is the true nature of the frontier Voyager is traversing and what else might be out there influencing it. The dark matter debate reminds us that the cosmos is still deeply strange, and the most exciting discoveries often lie at the intersection of known phenomena and total unknowns. A breakthrough in a seemingly unrelated field in 2025 provided a new lens through which to view Voyager's old data. For the first time, astronomers created a detailed map of the magnetosphere of an exoplanet. Using radio telescope arrays, they charted the magnetic bubble of a hot Jupiter, revealing its teardrop shape, its bow shock, and its long magnetotail being stripped away by its host star. This was a triumph of remote sensing, but its implication for our story was profound. It demonstrated that magnetic boundaries around celestial bodies are not simple, smooth shells. They are complex, dynamic, and highly structured, full of layers, reconnection sites, and turbulence. If an exoplanet's magnetosphere is that intricate, what about our Sun's mammoth magnetosphere, the heliosphere? The clean textbook image of the heliopause as a sharp boundary was already shattered by Voyager's messy crossing. The exoplanet map reinforced that this messiness is the norm, not the exception. It suggested that the heliopause is likely a vast three-dimensional zone of interaction, with filaments of solar wind mixing with interstellar plasma, magnetic islands forming and dissolving, and the boundary itself breathing in and out with solar activity. This new perspective makes interpreting the 2012 anomalies even harder, but also more freeing. A transient spike in data could be caused by many things within such a complex zone: a magnetic reconnection event, a passing solar wind shock, a localized instability. But it also means the zone is responsive. If a sizable object like an active comet ploughed through this structured plasma, it wouldn't just leave a simple dent. It would create a cascade of effects. It might trigger reconnection. It might amplify existing turbulence. Its own magnetotail might get tangled with the heliopause's magnetic field, creating a temporary localized knot of intense activity. The exoplanet magnetosphere map gives us permission to think of the heliopause not as a wall, but as a medium, a rich, structured plasma environment through which objects move. Voyager's instruments were sampling this medium. The anomalies were samples of its fine-scale structure. The question becomes, does the specific fine-scale structure seen on August 25th, 2012 match the kind of disturbance a comet would create, as opposed to the kind created by internal solar wind dynamics? This reframing is critical. It moves us from trying to prove a comet was there to trying to identify a comet's type of disturbance within a sea of other disturbances. It's a more subtle, but potentially more robust line of inquiry. It also points to the future. Just as we now map exoplanet magnetospheres, a future mission dedicated to heliopause imaging, perhaps using networks of small probes or advanced remote sensing from within the inner solar system, could transform our understanding. We could watch the boundary in real time, see its structures evolve, and instantly identify when something perturbs it. In that future, an event like the putative 2012 encounter would be immediately obvious. For now, we have only the single-point data from Voyager. But by understanding that it was sampling a structure as complex as an exoplanet's magnetosphere, we can better appreciate the ambiguity and the potential hidden in its old logs. The volume of data from decades of space exploration is staggering, and much of it has only been analysed in limited mission-specific ways. In 2025, as machine learning tools became more sophisticated, a team demonstrated the power of AI-driven re-examination of legacy data. They trained an algorithm to scan through the entire telemetry history of several older missions, flagging anomalies and correlations that human eyes had missed. The results were promising. Previously unnoticed solar wind structures, subtle instrument calibrations, drifts, and a handful of truly unexplained events. This approach is the key that could unlock the Voyager 3i Atlas mystery. Imagine applying such an algorithm to Voyager 1's data from 2011 to 2013. The AI would be trained on normal interstellar medium data and normal solar wind data. Its task? Find anything that doesn't fit either category. It wouldn't be looking for a comet per se, it would be looking for outliers. It would correlate the magnetometer, plasma wave, cosmic ray, and charged particle data in time, searching for multi-instrument coincidences that form a coherent structured event. It would then rank these events by their strangeness. The August 2012 anomalies would certainly be flagged, but the AI might find more, smaller precursor or aftershock events that humans dismissed as noise. It might identify a specific pattern, a magnetic spike, with a particular frequency spectrum in the plasma data that is unique. This fingerprint could then be compared to simulated data from a model of a comet's plasma interaction. Do they match? The power of AI here is its objectivity and its ability to process vast datasets quickly. It has no bias toward the heliopause turbulence model. It simply finds what is statistically anomalous. A human scientist can then take these flagged events and investigate them with physical models. This partnership is the future of archival research. For our story, an AI reanalysis could provide the definitive test. If the algorithm isolates the August 2012 event as the top outlier in a decade of data, and if the structure of that event matches a simulated comet flyby, the hypothesis changes from an interesting what-if to a serious scientific proposal requiring explanation. It could also settle the question of the 2024 glitches relation. Could the AI find a pattern in the corrupted data packets that suggests they were not random bit flips, but the shredded remains of a coherent but overwhelming signal? It's a long shot, but it's a question an algorithm could probe. The AI-driven approach represents hope. It means the answer might not require a new mission, just a new look. The data exists. The tools now exist. What's needed is the convergence of curiosity, funding, and interdisciplinary collaboration to point those tools at the right problem. The message might be in the archive, but the decoder ring might be a neural network. In 2025, the Sun provided a dramatic reminder of its power and its direct influence on the frontier. A colossal coronal mass ejection, far larger than expected for that point in the solar cycle, erupted. This was not just a cloud of plasma, it was a massive twisted rope of magnetic fields. When this structure, travelling at over 1,000 kilometers per second, reached the heliopause weeks later, it didn't just merge quietly, it slammed into it. Data from IBEX and the Voyagers showed the heliopause reverberating. The boundary oscillated like a drumhead. Pressure waves propagated back into the heliosphere and out into the interstellar medium. This heliopause ripple event was a watershed moment. It proved the boundary is not static or even slowly evolving. It can be violently and rapidly perturbed by solar activity. The implications for 2012 are significant. Solar activity in August 2012 was not at such an extreme, but it was not quiet either. The Sun was approaching its maximum in solar cycle 24. Could a smaller, previously unnoticed solar outburst have hit the heliopause just as Voyager was crossing, creating the observed turbulence? Absolutely. This is the leading alternative explanation, and it is a strong one. The solar outburst of 2025 provides a template. We now know what a heliopause disturbance caused by a solar event looks like across multiple sensors. Scientists can now go back to 2012 and ask, do the Voyager anomalies match this template? Do they have the characteristics of a solar-induced ripple, or are they different? This is a crucial piece of comparative forensics. A comet-induced disturbance might have a sharper onset, a different plasma frequency signature, or a more localized effect than a global heliopause oscillation caused by a solar shock. The 2025 event gives us a baseline for solar-caused, to compare against the 2012 unknown-caused. This new understanding doesn't disprove the comet hypothesis, it refines the debate. It forces the hypothesis to be more specific. It's no longer enough to say, Voyager saw something strange. We must now ask, did what Voyager see look more like a solar ripple, or more like a localized object interaction? The 2025 outburst ultimately underscores the dynamic and interconnected nature of our solar system. The Sun's mood swings reach out and touch the very edge of its domain. Any detective work at the frontier must now account for this fact. The true signal of an interstellar visitor must be disentangled from the background noise of the Sun's own powerful voice. In early 2025, another cosmic event punctuated the year. A brief, intense burst of ultra-high-energy cosmic rays was detected by observatories on Earth and in space. These particles, with energies millions of times greater than those produced in any human accelerator, appeared to come from a localized direction. Their origin was a mystery, a supernova remnant, a neutron star merger, or something else entirely. Like the dark matter stream claim, this event is likely unrelated to 3I Atlas. But collectively, these 2025 discoveries, the comet, the dark matter signal, the cosmic ray burst, paint a picture of a solar system embedded in a galaxy that is anything but static and empty. We're sailing through a sea that has currents, storms, and occasional flotsam from distant shores. The cosmic ray burst is a reminder that energy and matter from catastrophic events across the galaxy can reach our doorstep. The detection of 3I Atlas shows that physical debris does too. The putative dark matter stream suggests even the invisible scaffolding of the galaxy might have local structure that affects us. Voyager 1, at the edge, is exposed to all of it. Its data is a 50-year-long recording of this galactic environment. The 2012 anomalies might be one note in a much longer symphony of external influence. This wider view tempers the desire for a single, neat answer. Perhaps the 2012 event was a combination. A solar ripple and a comet passage, their effects superimposed. Perhaps it was something else entirely, an interaction with a filament of the interstellar medium that we don't yet understand. The importance of 3I Atlas is that it provides a tangible, testable focal point for the first time. It gives us a specific something else to look for. The burst of cosmic rays, the solar outburst, the exoplanet magnetosphere map, they all provide context, showing us that the frontier is a physically rich and exciting place, worthy of the kind of forensic scrutiny we are now applying. We have journeyed from a control room in Pasadena in 2012 to the discovery of an interstellar comet in 2025 through orbital mechanics, data glitches, magnetic signatures, and cosmic context. We have explored blind spots, sensor networks, and the powerful new tools that might crack the case. So, where does that leave us? Did Voyager 1 detect 3i Atlas? The evidence is circumstantial but powerfully suggestive. The temporal coincidence is striking. The nature of the anomalies, transient, sharp, multi-instrument, is consistent with a passing, localized disturbance. The orbital geometry, while uncertain, allows for a close approach. The lack of precovery images suggests the comet could have been dark and invisible, making Voyager's in-situ measurements the only possible record. The alternative explanations, solar-induced heliopause turbulence, are strong, but do not fully explain all the peculiarities of the data, leaving the door open. There is no smoking gun, but there is enough smoke to warrant a serious search for fire. The path forward is clear. It requires a coordinated, multidisciplinary effort. Orbital dynamicists to refine 3i Atlas's backward path with every new observation. Heliophysicists to reanalyze the 2012 Voyager data with comet interaction models. Data scientists to apply AI tools to find correlated signals across the heliospheric sensor network. It is a project that fits the modern era of astronomy. Data-intensive, collaborative, and driven by a specific, fascinating hypothesis. Beyond the specific question lies a larger truth this investigation has revealed. Our solar system is not an island. The Voyagers have taught us that the boundary is complex and dynamic. The discovery of interstellar objects has taught us that we have visitors. This story merges those two lessons, suggesting that our scouts at the frontier may have already met those visitors. Voyager 1 is more than a relic. It is a historical recorder of the galaxy's interaction with our star. Its fading signal contains not just data about plasma and magnetic fields, but potentially a logbook of galactic traffic. Decoding that logbook is one of the great scientific detective stories of our time. Whether the 2012 anomaly was 3i Atlas or not, the exercise proves a vital point. We must learn to listen more carefully to the whispers from our oldest, most distant explorers. They are telling us about a universe that is richer, stranger, and more connected than we ever imagined. The message from the edge of forever is not a shout. It's a subtle pattern in the data, a puzzle waiting for the right combination of curiosity and intellect to solve it. The question, did Voyager see it, may someday be answered. But perhaps the more important question has already been answered by the very existence of this mystery. We are not just in the galaxy is in us, its history written in the ice of comets, and the magnetic memories of our probes, and the story is still being written.